So I stripped all that out. Sorry.
It's okay. We forgive you.
Oh my God. Oh my God. Oh my God. I feel so guilty.
No, don't feel guilty. It's okay.
All right. All right. Jesus. But so and then Madeline, this was like a month ago, and we were like talking about what we were going to teach and everything, and I haven't taught this in 10 years, right? And Madeline and Griff and Ava, these the Madeline is another lecturer instructor, and then Griff and Ava are doing the labs, bless their hearts. And I just did not understand what was happening. And Madeline was saying, "Oh, I'm going to use sapling. I'm going to use sapling," and she used that word 100 times, and I did not understand what it was, you know. And I don't know if I asked or not, but basically, for the last couple of weeks, I've been like, "Oh my God, no one can get." I finally got access to sapling, right? And this is what sapling looks like. This is can you guys see sapling learning now?
Yes.
Yeah, okay. So when you get it, and has anybody gotten this?
No. No.
I'll take that as a no. So anyway, when you get it, it'll look like this. And I just can't get tech support anymore. It's impossible. So but when you get it, it'll kind of look like this. And then there are these homework assignments and stuff. So I will judiciously assign homework so that you guys can practice what we do in lecture, you know, and then we'll go from there, you know. And here, let's go to chapter 0. Like that's what we're going to do today, right? Chapter 0 homework, right? And then oops. And then when you get to the homework, it takes you to this damn, what is this? Oh, this is question 1, maybe? Oh, yeah. And you don't see this. I think it'll be more streamlined when you see it, right? But here, student preview. Let's go to that. I don't know to keep clear. I don't know. Just clear for now. And then when you get to student, it'll look like this. And then you can like answer these stupid questions. Which heavy metals is qualitative? Oops. And then how much is quantitative? And how much is quantitative? Da, 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 like this kind of thing, you know. And then but basically this is kind of like how you'll do it. And then you can check your answer, you know. It says, hey, you didn't answer this, but then it'll give you a hint, you know, or something. But that's sapling when we get to it, and I promise we will, but we need tech support. And so there's our syllabus. And then there's lots of very sort of ambitious steps here. And I kept the same midterm times as Madeline, and so that we kind of stay more or less and the same topics as Madeline. We'll see if I can keep up. No guarantees. But so that we at least have tests at the same time. Let's see. All right. So, what did I get on with? So, are there any questions so far, you know, basically about the course, how it's going to go, you know, stuff like that? So far, so good. Sorry, Alvin?
So far, so good, yep.
Excellent, excellent. Good. So, so I will switch to, okay, I gotta go to new share, and now I'm gonna go to this guy here, and we'll talk about the first topic. So what do you guys see? Do you guys see a single screen with the analytical process chapter 0?
Yes.
Okay. Okay, that makes sense. That makes sense. Good. Okay. So so this is one that this chapter basically it goes over how not to make horrific mistakes when you're actually doing an analysis, right? And I so wish I had just seen this chapter. I had a summer job basically. It was about maybe 12 years ago or so, and it was actually super interesting, and I got a lot out of it. But part of it was supposed to be I was going to do this analysis of silicon, 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 and I was going to compare these instrumental methods for analyzing silicon. And it was sort of a commercial thing where you say, "Oh, use our method," blah blah blah, right? And I got a bunch of silicon from this guy over at Stanford Research Institute. And then I got a bunch of ultra pure silicon, and we sent it out for analysis to a competitor, and we did the analysis in house. And the results were just ridiculous. They were just ridiculous. And we couldn't publish any of it because there's just no way to rationalize the huge differences in all these metals that we were finding in the silicon. So so that was a wash, right? And the reason that it was a problem was that I didn't do the analysis properly. And it wasn't really it wasn't really so much the actual instrumental analysis. That was fine, but it was the sampling. It was how we chose what actually went in the instrument, and that was a big problem. So we're going to check out here the analytical chemist job, general steps in the chemical analysis, and the steps are where I went wrong. So as another example here, we can say you can measure mercury in permafrost, right? And the way that you're going to do this is you're going to drill into these permafrosts. It's like you got to go to Alaska or something where the ground's frozen all year round, right? Then you drill a core sample, and you've got to do all this stuff to it, right? You've got to actually burn the organics out of the soil. Then you've got to trap the trying to get my son to make me coffee. But then you got to trap the mercury onto a gold surface, and then you desorb the mercury, and then you quantify it by ultraviolet absorption. So this is like an overview of like the analysis, right? Collect samples and measure them and everything, right? And there are two types of analysis: quantitative and qualitative. Quantitative is how much, and qualitative is what is it, and it's a real simple thing, how much, may answer, is there enough to be economically viable for like mining or something? And then, for example, there was a guy during World War II who decided that he was gonna pay back the fatherland by mining gold from the ocean. And he went all around the ocean in this boat, and they were collecting gold from the ocean, but there was never enough to make any money doing it. It always was like way more expensive to extract it. But that required a quantitative analysis, right? And then a qualitative is like, well, what's there? Is there gold there? Are you pregnant? That kind of thing. Okay. So let's take an example here, which is analyzing caffeine in a chocolate bar, caffeine and theobromine, right? And theobromine here is uh, it's it's a purine. It's a type of molecule very similar to the nucleobases in our DNA, right? And theobromine and caffeine differ by this methyl group here, right? And chocolate is really rich in theobromine, and it's has all these weird pharmacological aspects, diuretic, smooth muscle, relaxant, cardiac stimulant, vasodilator. Probably be good for me because since I've had a heart attack, if it's a vasodilator, that normally is good. So I'll be hopped up on chocolate here next time you see me. And then caffeine, which is stimulant. And so if you want to analyze caffeine in chocolate, you start by doing a literature analysis. And the real pure chemical way, the pure chemist's way, if you have access to them, is to use this tool called SciFinder. And SciFinder is a web-based program that searches chemical abstracts, which is just all the chemical journals, right? And SciFinder is a pretty good, powerful tool. And you'll use SciFinder in Chem 100W and possibly Chem 101. And it's pretty fun to use. But so you start with this process by seeing, well, how do other people measure these things in chocolate, right? The next thing you do is you sample, right? You buy chocolate or whatever, and then if you're really serious about getting a representative sample, like you really want to know the answer for something with some consequence like manufacturing or law or something like that, you need to measure a representative sample. Then you average over the many samples that you collect, right? And so you'll collect multiple pieces of the same sample and analyze a variety of different samples, right? And this process, this is one of the weird things I think about analytical chemistry, right? Because this is really like, you just have to think about it. Like, am I getting a good sample? Right? There's no mathematical recipe for this, other than say, take 100 samples or something, which isn't really a recipe. It's just like a guideline, So you have to think about, is what I'm doing representative of chocolate, for example? And then you can assess your samples whether they're homogeneous or heterogeneous. So homogeneous means the same, and heterogeneous means different. And an example here would be, it's chocolate that's the same everywhere, and this is different everywhere because maybe it has macadamia nuts or something in it, But like, you could also imagine like sampling a geological site, for uranium or something, and you got to choose a bunch of different random areas and do the analysis there to get a decent idea of how much uranium is there. So anyway, there's lots of different considerations here, and it's really an art, and the art of this is sampling, right? Then you can do sample preparation. Okay, so the sample preparation is part of the method that you'll find in, for example, SciFinder, right? And in this case, thank you, Robert. No water? No water? Oh, God. Okay, I'm drinking espresso. Can you guys see this espresso? Oh, Jesus.
Yep.
It's probably pretty good, but if you see me wince, you'll know why. Oh, wow. Strong. Oh, my God. So, now, turning things up. So, the sample preparation step in this case, let's just talk about it in detail in this case. we're not going to do this, so don't worry. It's not going to happen in the lab, so don't worry. But to get what we're trying to do is to get this chocolate into a form that we can inject into an instrument, you know? So we have to get all the insoluble junk out of it, right? And chocolate it's very heterogeneous. It has hydrophilic components, has sugars, it has hydrophobic components, has fat, caffeine and theophylline, millions of other things. It has completely insoluble stuff in there. It's like, bits of the beans that are all ground up, and so you've got to treat it extensively in order to be able to analyze it, right? So these guys, what they did was they used a mortar and pestle, and they actually froze it. I don't know how cold, if they used liquid nitrogen or just maybe dry ice or something. But they froze it really, really solid, and then they ground it up. And then they took this ground up chocolate stuff, and at that point you have to weigh it and put it into a tube, right? And then they extracted it with petroleum ether. Petroleum ether is it's just hydrocarbons like pentane and hexane mainly, maybe some some medium, actually some fairly volatile it's pure hydrocarbons. There's actually no ether in it. This is ether in the old sense of the word. It just means like volatile stuff, So you can use these really fine hydrocarbons, and then you just shake it up in there and centrifuge it, and then all the solids are going to go to the bottom, and everything is soluble in these light hydrocarbons are going to come at the top, right? And you'll have this defatted residue, right? Now, and what these guys did is they took this petroleum ether fraction, and they threw it away. And they only kept this, they called it defatted residue. So it's chocolate with no fat, right? And then they did then they dumped all the solids into boiling water, and then they boiled it to extract the caffeine and theobromine, and then they centrifuged it, right? And then they filtered it, and then they analyzed it, right? Now, so what comes through here has caffeine and theobromine from the original chocolate that we ground up here, right? But I want to point out a couple of defects in this method, right? I'm not being critical of Harris. Harris is a brainiac who is 50 million times smarter than me, trust me. But and so he's glossing this over a little bit, but I'm bringing it up because it'll come in later, right? And I want to get you guys thinking a little bit about this method. So, first of all, in this process of taking the ground chocolate, mixing it with petroleum ether, and separating it, and then throwing away the petroleum ether, what quality of the caffeine and theobromine are we relying on here to make sure that our analysis is representative of all of the caffeine that comes through this step? Does anybody have any ideas? Anybody want to shout it out there? So,
I'm sorry, Professor, could you repeat that one more time, please?
Oh, so what about this step here? About decanting the liquid and then using the defatted residue here. What about this step? Are we absolutely relying on in order to analyze all of the caffeine in the chocolate? Or what about this process here, right? Of shaking it. Right?
Sorry. Are you saying like we're relying on the liquid to be completely clean from any, like the liquid is just dissolved fat?
Exactly. And more precisely, it just has fat and has no what? Has zero what?
The theobromine and caffeine?
Right. Exactly. So let me ask you, does the petroleum ether have zero theobromine and zero caffeine?
Hey, Professor Jorge here. I would say that it can't because we're trying to dissolve likes with like.
Right. There's excellent solubility rules we can use, excellent things like this. But if I say zero caffeine and zero theobromine, then the answer here must be right, because these molecules, they're slightly polar. They've got these ketones, they've got nitrogens, right? But I can tell you that they're definitely slightly soluble in this petroleum ether, Not highly, but slightly. So probably a few percent of the actual result is getting lost here, right, in this first sample preparation step. And the way we're doing this, we have no way of knowing, right? So we are going to talk about a method, an analytical method, where we're going to know how much we lose here. Or actually, take it back. We're going to compensate for that loss in the method. Okay? And that method is called the method of internal standards. Method of standard additions. I get these confused. The method of standard additions, right? But for right now, let's just keep going here. So we've critiqued the method because we can say that the petroleum ether has some caffeine and theobromine here, right? And we're just losing it when we do this first step, And then the next one here, what are we relying on? For example, what are we relying on here and here and here? Right. We're putting it in boiling water. We're trying to extract the caffeine here. So if we take this guy here with water and insoluble chocolate residue, what is our assumption about this guy? Anybody want to shout it out?
There's some people answering the chat. I don't know if you can see inside the chat.
How do I get the chat?
There's like a button at the bottom screen, I think, like participants chat, share screen.
Okay, I'm going to find it. Thank you.
There's also, if you don't see like a specific chat button, you can hit the 3 dots. I think it should be over by reactions or the record button, and sometimes that'll bring it up too.
Oh, thank you so much. I'm so lame. Let's see here. Hide floating meeting trolls live on Facebook. Share computer sound. Breakout rooms. Closed captions. Oh my god. Wait. There was like some hotkey, right? Isn't it like Shift F3 or something weird like that?
It says Alt plus H for me.
Alt H. Oh, come on. You've got to work. Alt H, Alt H, Alt H. Dang it. Okay, hold on. I'm gonna see here. Speaker view. Gallery. Ah, there we go. I got it. I got it. Yay. Okay.
Woo.
So I'm gonna go back into presentation room. Okay, let me read some of these amazing answers here. So Omar says hydrophobic, shrugs. Excellent, Omar. Oh my God. Yes, we should form breakout groups, but yeah. Okay. Can you guys form breakout groups? That's awesome if you can. But oh, you're doing group me? That's awesome. I used to do that when I taught over the summer. Okay, so the idea here is that when you suspend the chocolate in the hot water, right, is that you're going to throw away. Next thing is you're going to throw away the insoluble part, right? So your assumption here is that caffeine is completely soluble in the water, and that no caffeine and no theobromine is lost in the solids, right? And so this is actually false too. That's a false assumption because caffeine is not super soluble in water. Maybe a little hot water, but maybe hot water helps, right? And then there's the filtration step. Does any of it get absorbed into this stuff? Yes, obviously, probably a lot less. Probably thousands of a percent here. But anyway, so there are issues with the analytical method. And I'm sort of emphasizing them here because it's really a lot more interesting that way. Honestly, it's so boring otherwise. So, and we're going to show you how to do this later, right? So, now the last thing we're going to do is we're going to take that solid, that particulate-free solid, and we're going to do chromatography of it, right? So, in chromatography, this is writing with color. It's basically separating the different, physically separating the different compounds in your sample, right? So we're going to inject this extract, this water extract of, this water extract of caffeine onto the column, and then this sort of plug of stuff, we're going to drive it through the column with some water, right? Or it could be water and methanol, or water and acetonitrile is another solvent that's used here. And the idea is that this column, and typically it's like 4 millimeters in diameter, is packed with silica, SiO2. These basically pure glass silica particles that have on their surface, just the surface of the glass, is coated with a single molecular layer of an organic compound, for example, octadecane, which is CH2, 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 17 times CH3, right? So you can coat the surface of the silica with octadecane, right? And then you drive this this mixture of water and the components of chocolate here through the column, and then it goes to waste. And as things leave, you see them in this system here, which has a UV lamp and then a detector, right? The UV lamp shines through this capillary, and the detector picks it up as it goes by, right? And so you get this signal from the detector, right? And you pipe that out to a computer, right? And then what happens is that as the different components go through, some of them go through more slowly than others, right? So the caffeine here has that methyl group on it, and it's just slightly better at interacting with the octadecane than the theobromine is, right? So over time, as these elute, that's the expression that we use for this coming out of the column is elution. As these analytes are the things that we're measuring, the analytes elute, then you see them come out one by one, right? And you know, in this case, it's a pH dependent phenomenon, right? So if you have acid in there, it'll protonate the silica surface. If not, it'll tightly bind them. And this is basically for the silica that's unmodified. We don't really care about that here. The thing that we care about really is that things come out one by one in an intelligible order, right? That the most hydrophilic come out first, is where the solution is hydrophilic. It's basically mostly water. And then they come out and blah, blah, blah. And then what you see is you see a lot of minor components come out. Then you see a huge spike. Huge could be, tenth of an absorbance unit or something like that. And then you see a smaller spike for caffeine. There's something else here. We don't know what it is, right? And chromatography is what we've just described. The analytes are detected the outlet because they absorb UV radiation from the lamp, right? And then the graph of the detector response versus time is the chromatogram. And the you can take a spectrum of things as they come, or you can add, for example, you can intentionally add caffeine and see which of these spikes grows, or you can put pure caffeine in and see at what time caffeine will elute, right? These are ways that you can sort of get out of there, right? So now once you've done your sample, right, and you get this chromatogram with several peaks, you don't actually know which one is theobromine and which one is caffeine, right? You can guess, but you don't actually know. So the next thing to do is to calibrate, do a calibration or a standard curve. So calibration is a method of linearizing your detector response versus analyte concentration. Excuse me. And then, so you put in, say, 10, 25, 50, and 100 parts per million of caffeine. So that's 100 parts per million would be 100 milligrams of caffeine per liter of solution, or per milligrams per kilogram, really. Milli per kilo. That's a difference in a million, right? That turns out to be milligrams per liter if you're doing it in water, right? So you can calibrate it both with caffeine and theobromine. You can put them both on the same plot here, right? Then you can integrate, and you put the integrated area here, or the height of the peak, whichever one you can get to, right? And then you make this graph, right? And then you when you get your unknown, you find its peak height here. You draw a horizontal line out. then you draw the vertical line down rather, and then you get the concentration of the analyte, right? It could be caffeine here, or theobromine rather. You get the concentration of the analyte on the x-axis. So how are we doing here? Does that make sense to everybody? That was like a long discourse, sorry.
It was good.
All right.
Okay.
Anybody like pissed off because I'm unintelligible, too fast, too slow? Okay. Actually, if you're pissed off, don't tell me. Just kidding. So, all right. So then you can do the analysis. It's all kind of, weird stuff you can do. And then ideally what you want is you want a good uncertainty with every value, right? So you can calculate the grams per 100 grams of chocolate, right? Grams per 100 grams is also known as percent, right? Percent is per 100, right? So 0.392 grams per 100 grams is 0.392% theobromine, 0.05% caffeine, right? And here we have 0.392 plus minus 0.002, right? And what this means is that here's the answer we got. And here's our best estimate of the uncertainty in our answer, right? The uncertainty in our answer is what we guess that the variation for a series of identical samples will look like, right? So if we had, 100 identical samples, we put them in, we would not get exactly the same answer every time. Rather, we would get a distribution with a width. I say width of distribution, right? I'm referring to the histogram here, but we would say that from the lowest to the highest, about 67% of them would be within 0.002 of the average. So that's what this means. So uncertainty is a very important metric to include with your analysis, right? So this is 0.392 plus minus 0.002 is equivalent to saying 2 out of every 392 is our relative uncertainty. So call that 2 out of 400. That's about 0.5% uncertainty, right? Caffeine has a higher relative uncertainty. That's about 3 out of 50. That's about 6% uncertainty, right? So, but both of these are quite successful, right? Now, in order to quantify these same two things in white chocolate, we got 0.010 plus 0.007. In this case, it's very likely that this answer would be possibly detectable but not quantifiable. And the same is true here, right? This might not even be detectable. This might not even be a detectable amount of caffeine, right? So that depends on the statistics of the answer, whether or not you can say that. But when it's 70% uncertainty, or like 15% uncertainty here, then you have to ask yourself, well, is this actually detectable? So anyway, there's what we get, right? And then you can compare them to other things. And this is like how you would go about analyzing the data, right? So you would look at the data, compare it to other things, right? And coffee, you get 160 megs per serving, And so This is one way to analyze your data, and then you can try to draw conclusions from this data here, if you want. Right now, there's other ways to do this. For example, this is a really cool way of both of combining all of the 3 steps of the petroleum ether extraction, the filtration, and the water extraction. Right, is you can put the crude chocolate. This would be the ground up chocolate that's sort of dissolved in petroleum ether. Put that solids and all onto called a solid phase extraction cartridge. Right? First, you condition it with methanol and water. You apply the crude sample. Then you can put a weak solvent through here, right? Oops. And then that shows sugars coming out, right? And you can put a stronger solvent through, and then the idea here is that weak to strong is something in which the analytes here, the analyte has the star, that's a component of the mixture that we're putting in, that will come out with the stronger solvent, that is the solvent in which this component is more soluble. That's the idea of a weak and a strong solvent. A weak solvent won't dissolve it, and therefore it will stay on the solid phase extraction column. Yeah. And then as you put the stronger solvent through, it will elute. So here, for example, is an example of that. You can take a solid phase extraction column. There's a filter at the bottom. There's a bunch of this HPLC stationary phase here. And then there's a bunch of solutes on the top here, right? And then you're going to add water, or actually, it's water with a little bit of isopropanol, right? And then you start eluting it, and you notice that the red stuff comes off really quickly, right? Then you're going to ramp up the isopropanol, right? And then pretty soon all the red is going to come out. You're going to just have the blue, right? So you go from 4 to 5% isopropanol, and then you finish it with pure methanol, right? Pure methanol will elute the blue stuff, right? And so this is how you would separate these two on a column and also get rid of the solids, right? This is just an example of a solid phase extraction, right? And in general, what we've done here is we formulated a question, right? It's like, how much caffeine is in chocolate, right? It could be, the question though is important, right? And it's important basically to think about this, and it's actually best to think about it with others. Really think about it. And it's a thorny, nasty, qualitative problem to formulate the question, right? But it's very important, because when you're done, all of the things you do will answer this question, possibly more, but not definitely more, right? So formulate the question, and then select the procedure. Use SciFinder for that, or Google Scholar or whatever. SciFinder works really well. And then you're gonna sample, meaning you're gonna take the samples from the field, right? Prepare the samples, basically extract them or whatever, analyze them on the chromatograph, right? Then you're going to make a report and draw conclusions from it, right? And that's all that the analytical chemist does. I mean, this is a lot, actually. Most practical analytical chemists will basically be, maybe we'll sample, probably we're going to prepare, analyze, and report, These are the main things that we're going to do, prepare, analyze, report. But if you have greater responsibility, then you have to do these other parts too, So anyway, blah, blah, blah. I think you guys have seen this already. And then, and then the sample can be heterogeneous. It can be heterogeneous or homogeneous, right? And most likely they're heterogeneous, right? And when they're heterogeneous, but they're like extremely heterogeneous, right? Where there's different patches of different compositions in the material. This is like chocolate with macadamia nuts and like some other crap in it here, you know. And like if you have a sample like this, it's called segregated heterogeneous, right? And random heterogeneous. And then if it's random heterogeneous, then you can just take samples, right? Take, 10 or 100 samples from here, right? And then you number them, etc. And in this case, you're going to have to do much more sampling. You're going to have to be very mindful of which areas you're taking the sample from. That's from a segregated heterogeneous and then a random heterogeneous material. These are just names that we have to remember, right? This only comes up once in the class, but there'll be probably a question like this on homework and stuff like that. So, all right. So, just real quickly, the analysis is meaningless unless you properly collect samples, measure, Chemical analysis is only the middle process that begins with a question and ends with a conclusion. So, that's all I have for you today. And I will upload this PowerPoint to Canvas for y'all, and then I will see everybody out on Tuesday again, right? And hopefully, just keep an eye on the Canvas, and I'll let you know when I hear back from these jokers from Macmillan about how to get everybody onto Canvas. And also, I will upload a link to the video that we're recording as we do the lecture. So that is one of the beauties of this, is you don't actually have to get up for a class, although I really appreciate it if you do. All right, everybody. Any last questions? Complaints? Insults?
Do we have a set date and time on which we're gonna have exam, or how is that gonna work?
Yeah. So the exact date and time of the exam, I think they are actually in the syllabus, but if not, I will make sure and get them out to you. So it's in weeks. It'll be the Thursday of week 7, right? And I'll give you a midterm. And I'm not sure we're going to do ours by take. I just feel like those are so open-ended. So I'm not really sure about that. We may do these using the stupid Respondus browser or something like that. I'll kind of take a poll, see what people like, but it's like pretty messy. But we'll do Thursday of week 7, Thursday of week 12 for the exams, and I will give you plenty of heads up on that. All right, and then also the homework. Let's see, homework is going to be sort of like in the home part here, right? Home. We'll find our homework. These are going to be due. This is just to read the stupid syllabus. Then Thursday, I do the first sapling homework, and it's for the chapter that I just went over. Alrighty, guys. Okie dokie. I got to wrap up now. Please, I'll be back online at noon today for office hours, and then I will see everybody next time or as soon as possible.
Thank you.
Thank you guys for listening. This is so
Professor.
new for me, but thank you so much.
Goodbye.
Okay, guys. Bye-bye.
Bye.
Bye.